It's the third and last tutorial that Stephan is going to present, and he's going to show tutorial related with Valleytronics. So Stephan.
Okay, thank you. So what I want to try now is to connect with this additional degrees of freedom that we have in this two-dimensional material, and that gives rise to the this Valleytronic phenomenon. So first of all, I remember that if we just consider graphene without disorder, without spin-orbit interaction, then we have a system. The wave function is actually a 8-component wave function, and we have, in addition to the spin, which is a very peculiar property, we have the Valley pseudospin or isospin, as you like, and the sublattice pseudospin. So these 3 degrees of freedoms are completely described by the same mathematics, and they can add a contribution to the wave functions, and they can be detected or can be modified by the geometry of the system, for instance. So graphene has this inversion symmetry, which keeps the degeneracy between these 2 valleys, but we can play with that. We can open a gap. For instance, in the case of a bilayer, for certain stacking, you can open the gap, and then you change the on-site energy on the 2 layers by an external electric field, and you can tune this gap. Then boron nitride is another situation where there is breaking of the inversion symmetry, and so this result due to this electronegativity with boron and nitride in a much larger gap, few electron volts, 5 electron volts, and so forth. And now with the case of TMDs, a strong spin-orbit coupling additionally induced this spin splitting of the bonds. And this case is particularly interesting because we can start to have valleys. The 2 valleys have a different spin textures, so it starts to be a very interesting knob to design new type of property. So it has been very early on, for instance, Carlo Binacker, from the theoretical perspective, he proposed the way to filter valley, degrees of freedom in graphene. And then I think this work was initiating a lot of interest and a lot of work, a lot of experimental research in order to control optically the valley degrees of freedom. So this work of Xiao, Yao, and Niu was considering actually a graphene with a broken inversion symmetry. Could be a substrate, and in this situation, they derive their Berry curvature and found that it has an opposite sign at the 2 different valleys of the graphene. So this difference in Berry curvature actually result in the semiclassical transport equation in an anomalous velocity which separates charge depending on their valley index. There is also a similar theoretical concept for the spin-Hall effect. So this was the basis of the valley Hall effect that were proposed by these people. Of course, it supposed that there is extremely weak valley mixing, otherwise you lose this, what can I say, well-defined quantum index. And but by the electric field, you could generate a similar to the spin-Hall effect. You could generate this accumulation of valid contrast state at the boundaries of a system. And actually, what they proposed in their paper was to valley filter somehow with the kind of zigzag ribbon in between 2 graphene leads, and to measure some kind of signal that would be really valley dependent. So the discovery of the properties of TMDs at a single monolayer level has been actually more efficient to move forward to the control of Valley index. So in this case, broken inversion symmetry, and we have this massive Dirac fermions, so parabolic bands. There is a big difference in the electron property with the gap, with the fact that the splitting is also gigantic for valence band, and that between the two different Valley index, you need, if you want to switch from one Valley to another, you need to flip the spin. So-called spin Valley locking. So this means that you have possibility, for instance, if you shine light and you create excitons, it was shown that the polarization of the light in the circular symmetry, clockwise or counterclockwise, will actually be, by selection rule, exciting the creating the formation of an exciton in one valley or another one. So it means that by light you can create a valley polarized exciton pair, and you can also make a combination of circularly polarized and get a linear superposition and get, so somehow you can tune your property of your excitonic pair depending on the initial symmetry of the light. So this, I think, was a major breakthrough, that people realized that this could be accessible because of the large spin splitting, and that under light absorption you will generate, what I just said before, different type of excitonic properties. So actually this phenomena has been revealed. Probably Roland will enter into the detail. I would just flash this. Somehow by this optical experiment, this CARE experiment, rotation signal, it was identified similarly to the spinel effect, that you could accumulate Valley information at the edge of your system. And also I think this experiment is a kind of first evidence of the Valley effect by electrical detection. So I will not enter into the details. Probably Roland will come back to that. One result that is particularly interesting is the fact that actually once you create this excitonic pair, if you have a driving force to drift them away from the source of excitation, then you may observe a kind of exciton Hall effect, in the sense that depending on the valley you prepare your exciton, you will get a drift on one side, on the opposite side for the other valley. Actually, this paper is very interesting. I think if you read the conclusion, you will see that it's absolutely unclear what is the mechanism behind this drift. I mean, and what kind of exciton actually are drifting away. So there is clearly a thermal gradient that is generated because the excitation is just in part of the device. So this thermal gradient is likely to provoke that. But what is exactly the spin component? Is it a neutral exciton, charge exciton, trions? If it's a charge exciton, it will have maybe a different dynamics, and there is a spin orbit coupling field inside the system. So just by if you're interested, just look at the conclusion, and you will see it's very open. And of course, exciton physics in this material is quite it's very challenging, etc. And Roland will probably point out. But I think this is an extremely interesting result, which demand for more analysis, and especially what we don't really know from the theoretical and computational standpoint is to compute, to look at this dynamic of the excitons in real space and in time. So that's something very interesting to investigate in the future, and to understand if this exciton Hall angle is tunable, to which extent, and so forth and so on. To come back to the initial proposal of Yao and Yu, they want to break the sublattice symmetry of graphene, and one way to do that is to actually to deposit graphene on boron nitride, and by proximity effect, you will differentiate A and B site in graphene, because they will interact differently with the substrate. So there is somehow a very stable situation which can create a very large gap, the order of 30 millielectron volts. But you have also many more different type of commensurate stacking, which create moiré pattern. And actually in this situation, the gap is not completely homogeneous. We'll come back to that later. But so in this situation where you have a full gap, in principle, the argument and the proposal of Yao, Xiao, and Niu could be in place. We could measure a Valley Hall effect. So that was
Stephan,
reported.
Can you go one back? So this is for this central hexagon.
Yeah.
No? Okay.
Yes, well, you have the boron, okay, which are
okay.
on the top of one carbon, like a sublattice, and the nitrogen is too far from the base sublattice. So it's a complete breaking of the. It's a stable configuration, but okay, you have other type. In other type of commensurate alignments, you create a different moiré, which does not result in a full band gap. So this experiment is actually by Andrei Geim and Novoselov and Gorbachev was actually aimed to test this Valley Hall effect physics. Okay, so they made these non-local transport measurements where you have your current in one of the probes, and you measure a non-local voltage away from the current flow. And the idea is that following the concept of the Valley Hall effect introduced by the paper will be that you separate only this K valley will go left and K prime valley will go right, for instance. That's the idea. And this is what they measure in the non-local resistance. Very, very large peak at the Dirac point, a satellite peak which is related to the moiré of the system. And also in this experimental data, we see that this completely random stacking, non-aligned, non-commensurate, will result in zero response. Okay, so it's kind of going in the right direction. Their non-local voltage also in this case is decaying with the channel length. So that is, this valley information is lost at some point because maybe of scattering, because of edge boundaries, and as soon as you have inter-valley scattering actually active, you lose this Valley Hall effect. So the experiment suggests extremely large, actually giant Valley Hall angle in such a situation. Okay, so I will come back to this in a moment, but I'm again mentioning this work of Roland because here we have like all the ingredients of this controlling valley, controlling spin, transferring spin information to another two-dimensional materials, and so forth and so on. So again, this is a milestone paper. So there is also, when you go down in smaller size, let's say like graphene, quantum dots, so you have the valley, these valley degrees of freedoms again comes into play. And this was a very interesting work of Guido, Hoffling and Guido, where they say this additional valley degree of freedom is interesting, but it will make more difficult to design quantum gate. So, for instance, they mention here that this spin valley entanglement will make much more complicated to make a C-naught gate. So in their calculation, there was no spin-orbit coupling included, but of course you can including that, and then the situation is quite heavy, and there have been a recent proposal about spin valley qubits, but I think this is not so much investigated, unfortunately. But here we have entanglement, more degrees of freedom to play with, and to maybe engineer more efficient qubits. So now what I want to do is just to, like the spinel effect, I want to make some kind of description about some issues in the interpretation of the experiment, and then we'll go also to some discussion about the quantum Valley Hall effect, just to be a kind of mirror talk with the first one. So again, I'm pointing out this experiment because I've been also involved in trying to understand the origin of this giant resistance, and to investigate the scenario that was proposed to explain such a feature. The point is that it has not been, it has been reproduced somehow by different groups using, for instance, bilayer graphene. And if you, this is a list of the paper, and actually if you read all the papers have a different, mostly different interpretation. So interpretation change in time. For which reason? So the reason is that the initial model that was kind of, let's say, extension of the new Yao proposal is the following, proposed by Levitov and Song. They say that if there is a gap, if we are in this situation with full commensurability and this A-B stacking, and we have a gap, we can describe the Hamiltonian simplified low energy version with this Dirac part and just the gapped term. Okay, so we can make this calculation of the Berry curvature, and what we basically say is that we will have the Valley Hall current emerging from the when we have an electric field, and so there is a possibility to connect semiclassical transport theory, the non-local resistance, to this Valley Hall conductivity, the resistive longitudinal resistance, and so these are parameters of the device, and this LV is a Valley diffusion length somehow. What is the propagation until you mix valleys and you lose the phenomena, and then you will have reduction of the non-local signal. So through this theory, they got some direct connection between this Valley Hall effect, which is purely intrinsic from this Hamiltonian, let's say, and then with the signal that is measured. The point is that although we can measure this non-local resistance, we can in the experiment, and we can also evaluate this directly, the resistivity, we cannot really measure the Valley Hall conductivity. And we cannot measure it from optical measurements. And there is no readout, electrical readout of the Valley degrees of freedom. With spin, we can, because we can play with the magnetization of the contact. And but in the case of Valley Hall effect, how can we discriminate between a non-Valley dependent signal and a Valley dependent signal? So, however, from the theoretical point of view, we can compute this quantity independently, and so we can try to investigate if this relationship between the Valley Hall conductivity that will be driven by some bulk property and Berry curvature and so forth and so on, is the quantity of relevance to explain the non-local resistance signal. So this is the result of this discussion with Branislav again, and I put a photo here because, as far as I remember, these calculations were very computationally demanding, so that was a lot of efforts from Branislav to end up with something, right, as far as I remember. So here, what I want to say is I want to show is that we try to make the simulation of the non-local resistance, designing a model that will be as realistic as possible. So we have the channel where you have the full alignment of your graphene on top of boron nitride. You have this configuration, multi-terminal configuration. You force the current to flow here between 3 and 4, and you measure your voltage between 5 and 6. And in order to move into the modeling, there is a need to combine some full ab initio quantum transport simulation with a simplification of the model to type banding. And then we can go to much larger scale of the simulation and so forth and so on. And we can also compute the Valley Hall conductivity in the bulk limit. So this is the result of the simulation in the case where we don't consider the full, more realistic model, but we just take the simplistic Hamiltonian, in which we just have a gap term, and we compute both the non-local resistance signal and the Valley Hall conductivity. So with, for the pure case and with some kind of disorder. So indeed we get a Valley Hall conductivity, which is a signal of Valley Hall effect, which is finite because of the presence of the gap, okay? But when we look at the non-local resistance, actually, even though for very short channel lengths we can measure some kind of signal, when we enter into more realistic channel lengths compared to the experiment, this signal is totally suppressed. Okay, and it's basically suppressed because in the zone where there is no states, there is no reason why we could have a Fermi surface signal. And in the model, the phenomenology of this model, the authors assume that although this Valley Hall conductivity is a Fermi C contribution, it will have some extension in the gap. And this is what we measure. So kind of scenario which contradict what can be simulate brute force within the Landauer-Büttiker multi-terminal regime. So it means that if this formula that is derived disregarding the contact and just based on semiclassical transport theory is, according to our simulation, is not applicable for exactly this model with an homogeneous band gap. So, but however, we can try to see to which extent we can get some more understanding of that. So in the experiment, there is something interesting, which is this peak at the Dirac point, and in order to get this peak, we need to go beyond the simplistic approach. We need to go to this realistic model where we have edges, where we have really the graphene underneath and the HBN underneath. And when we do this simulation with the most realistic model, then we indeed get into the gap zone this large non-local resistance signal. Okay, so this is the gap size. Here we have the things. So although we have a gap all along the channel, we get a signal inside the gap, as in the experiment, presumably. So sharply peaked. We also get some dissipative resistivity that we can calculate. So we can try to see if this phenomenological formula, in this case of more realistic modeling, is actually possible to discuss, to connect with, right? So indeed, as in the experiment, if our channel length is increasing, then our simulation, the non-local signal, will decay as soon as we have some disorder at the edges. Whether if the system is super clean, then the signal will be maintained for very long. So we find an origin of the loss of the information. But the explanation of the result of the simulation is not related to a bulk-driven Valley Hall effect, but it is explained by the formation of edge states, which have, as we show here in the figure, which have a special kind of dispersion. Usually zigzag ribbon, for instance, there is non-dispersive edge state. In this case, we have a dispersive state. So this dispersion is at the origin of the possibility for transfer of information inside the channel. And so this is, for instance, this is a plot of the local density of states. So we image those edge state and their robustness with respect to edge disorder or bulk disorder, something like that. Also, we need to have a special symmetry of the edge state of the graphene edge termination, because in the case of an archer edge termination, basically the system is really gapped and there is no edge state formed, and so no signal is propagated. So that's somehow it's a totally different interpretation from the initial Valley Hall effect driven signal. It has to do with the formation of states that are not really topological, but that are related to the geometry of the device and to the interaction between the graphene and boron nitride. And it's supposed to be also in a certain edge termination, which might be plausible in the experiment, but it's still a question of robustness, actually, to, for instance, a full armchair termination. So there is still a debate about the interpretation, and I'm just pointing out, I will not enter into the detail, but this is a very recent work of Song and Vignale, where they find a kind of edge state in the bulk, so which is a bit difficult for me to understand, but yeah, they have some arguments and an alternative interpretation of all this. But I will show some of our recent ideas about an alternative interpretation, new interpretation. Basically, come back to this experimental data about the signature of the interaction between graphene and the boron nitride in the moire. So here, look at more general situation of commensurability between the layers. And so these peaks are very important because they tell you how to estimate the moire, the size of your moire supercell, for instance. That will depend on the commensurate, on the angle. And actually, there is a very nice model that has been developed by Sack and company, Katznelson, where they did a very careful DFT studies, which is very complicated as far as I understand. Some expert here in the room, because to take into account long range, van der Waals interaction, and especially to compute the stability of the system, you need to go like beyond the conventional DFT. But eventually, this calculation end up to image what you have in a different commensurate case. And this is actually a very important result, which is the local gap that is created in relation with the moire pattern. So it's not completely homogeneous, but it's a line in the system depending on the geometry of the moire. So they even have a simple model then to describe the electronic structure, which introduces spatial dependent mass term that you have to introduce to take into account this inhomogeneity of the gap. Okay. So there is a way really to then to describe based on this model. You can look at the density of states. You can get this resonance that are related to new secondary Dirac bonds related to the moire. So, and then you can confirm that actually these positions are completely in agreement with the experimental data. So this peaks is depending on the size of the moire. So the model is, then the model can be made very accurate, and we can do a simulation where we can reproduce, not exactly, of course, but we can reproduce this appearance of emergence of the Dirac, secondary Dirac points, and all the resistivity is sensitive to these features, new features, when you have disorder included into the system. Okay. So now, what we have as a new idea is that maybe this situation allows us to reconcile the existence of the Valley Hall effect, but not as a, let's say, intrinsic Valley Hall effect, but as an kind of extrinsic Valley Hall effect. So what we consider is that in the system we will generate some patches of dots where we will have a mass term, and we want to see how this can generate a kind of bulk-driven signal, which will be Valley dependent, similarly to what I have shown for the thallium island, generating some H-state chiral, bulk chiral current, and eventually a possible quantum spinor effect signature. So I'll go quite fast. This paper is even not on archive, but is it on archive now? So what we can do with that, having this dot, actually we can calculate the degree of local Valley polarization of the scattered current, because actually this mass term is acting on A and B sublattice, and it turns out that if we look at incoming state and the scatters, then we can actually generate this Valley current by this local inhomogeneous mass term. It's a lot of information, but we can try to investigate as a function of energy all this Valley-dependent scattering strength is scaling, and with that we try to connect this to the Valley Hall conductivity that I've shown before, and then we can compute from the bulk information. So this is a calculation. All this Valley Hall conductivity will scale in the situation where you have a full uniform band gap, or you have these dots distributed in the system, and we show actually that the signals will decrease with the size of the moire, for instance. What is, however, interesting is that differently to the uniform case, where there is a real gap and there is no Valley Fermi surface contribution, so if you look at this at the zero energy, the Valley Hall conductivity as a function, let's say, of the disorder, we get vanishing contribution of the Valley Hall surface, Fermi surface Valley Hall conductivity at the Dirac point, whether in this case of non-inhomogeneous mass term, we get a signal that actually increasing with reducing disorder. Okay. So this is an interesting signature because it shows that there could be a bulk Valley-driven signature of these Valley currents.
Stephan,
yeah, question.
So, so you plot?
Sorry, I'm going a bit fast. Yeah, this is actually this eta is a broadening term, which is presumably describing a very weak disorder.
Okay.
So actually, if this term is very large, I mean this term is very small. So we have very small broadening. But okay, for people really interested in that, the main difference is that a full gap or an inhomogeneous gap will differentiate the possibility to measure, to have a finite quantity related to Valley degrees of freedom at the Fermi surface or not. So that connects with what I said before, and that is an alternative explanation of the experiment of Manchester, to our opinion. Okay, so what about the quantum Valley Hall effect? Because what I show is kind of emerging bulk-driven Valley Hall effect. But quantum Valley Hall effect has been also proposed in the literature from the experimental colleagues. Actually, they claim that once the system is actually extremely clean, so the mean-free path is very long, and you have a gap, then you will not have any state in the gap. So I agree with that. So what you should have is Valley polarized H state, exactly the same analogy with the quantum spin Hall effect. Okay, and so they measure non-local signal, and they got some numbers that, although it's not plateaus, so it's not super convincing, they are not plateaus, but the values are close to the expected values for the plateaus in such a regime of quantum Valley Hall effect. So this is debatable. I mean, this is like not really understood, and the claim of a quantum Valley Hall effect based on this type of experimental data is a bit maybe complicated to validate, right? What I want to show is, because it turns out that the quantum Valley Hall effect is something that would be also very interesting, but it turns out to be not trivial to achieve. And I will show one example that is very academic maybe, but where we could achieve without any ambiguity a quantum Valley Hall effect, and what would be the consequence in transport. How can we unveil this in experiments? So this is related to the possibility to, with strain, to create this pseudomagnetic field. Okay, so that was introduced by Paco Guinea, Carstensen, and Andre. Well, they were showing that when you strain your graphene in with a certain symmetry, you can generate an effective pseudomagnetic field, which, however, does not break time reversal symmetry. Okay, so it means that if you are in the graphene, when you switch Valley, you switch the sign of this pseudomagnetic field. So the sum is 0. We cannot have an observable consequence in terms of quantum transport. But you can probe, however, the formation of pseudo-Landau level, even experimentally, and that was their proposal, that this triaxial strain field, you should create an homogeneous pseudomagnetic field of very large intensity that could be probed by a STS, for instance. And as far as we know, this has been confirmed in this experiment, where they got kind of graphene bubbles with exactly the symmetry that was proposed theoretically, and they measure a signal of the local density of state, which their extrapolation to the theory conclude to a magnetic field in the order of 1,000 Tesla. So that's also very attractive, because again, it's like the spin-orbit coupling field. It's a field that might allow to play on the other degrees of freedom, like the Valley, without a real magnetic field. So for Valleytronics, it would be very interesting to have this kind of strain field deformation controllable. So Michael Sitness showed that if you exactly have this kind of bubble, what you have is if you have a transport or like incoming wave packets, for instance, with an equally distributed contribution on both Valley, what you have is you filter the Valley. Another observation is that making this type of strong deformation, and people, you are very inventive from the experimental side, and there have been several proposals, like depositing graphene on top of an array of nanowires, or even chemically, there have been observation of superlattices of these valley bubbles. So this is really appealing. And this is one of the last work already published where they have graphene on a substrate which strain the graphene and they create trenches. And they also estimate 100 Tesla pseudomagnetic field of a nanometer scale. So there is a lot of engineering, and certainly people need motivation or need to measure something to demonstrate that these pseudomagnetic fields are really useful for something. So what we actually realize with Michael is that if this pseudomagnetic field is creating is opposite in the both valley because of time reversal symmetry, what will happen if we just add a real magnetic field on top of it? In principle, we should double this magnetic field in one valley and we should suppress completely in the other valley. Mathematically, there is no reason why we can play with the gauge in this way. So this is what you get if you have this pseudomagnetic field. If you look at compute the density of state, you get your Landau level, zero energy Landau level, and then it is the higher energy Landau level are spaced following the Dirac, let's say, physics. So you can check about that. And if you have a real magnetic field which is added to it, okay. So as I say, with this simple picture, in principle, one of the valley will be, there will be no gauge, will be absolutely transparent to this magnetic field. Whether the other one will just evidence the formation of Landau level, or Landau level superposed to pseudo Landau level. And this is what we see here. This valley K is completely silent. It's completely usual graphene dispersion, whether in the other one we have an Landau level. So what then will be the signature if you want to measure, for example, the whole conductance, the quantum regime? In the situation where we have a real magnetic field, you expect your quantization of the conductance. In the situation where you just have a pseudomagnetic field, you would expect nothing. You expect nothing as a measurable quantity, because there is no time reversal symmetry speaking, but this nothing is actually something that suppresses something with a different sign. Okay, like the Berry curvature with a different sign in two valleys. Here we show that we can valley project the conductivity, so valley roll conductivity on the K and K prime. They are not zero, but their superposition leads to a zero signal for the total whole conductance. Okay, so the valley roll conductivity is not unobservable if we have not broken time reversal symmetry. But we have this kind of picture. So now the question is what happened, and can we measure some signal in case we have superimposed these two magnetic field and pseudomagnetic field, which is exactly the situation here. And here we see that the valley resolve conductivity is completely different. In this case, where there is no magnetic field, we have zero signal, more or less. But in the other case, we have your plateau, but with a value of the conductance that is reduced. So we have a very interesting situation where something can be measured. It can be switched on and off. If you, for instance, if you have already your pseudomagnetic field established and you switch on and off your magnetic field, so you could have a plateau that will move up and down. And in addition to this, and this is really quantum valley Hall effect, we will have a fully polarized DC transport. So we picture here, when we have the plateau, okay, due to just one valley, we have a dissipation in the other valley because there is a finite density of state, so there is a finite longitudinal conductivity, but completely valley polarized. and you have a plateau that is determined by the other valley. So it's a kind of very funny story, but I think that it's kind of maybe also a generic way to engineer some quantum variable effect, because otherwise it's not observable. It cannot be measured if you don't break time reversal symmetry. So actually, we also shown this paper that this result was quite robust to additional disorders superimposed to the system. So yeah, this part of the talk is a bit shorter. What I want to respond to the question, because there are some parts that are a bit like more, maybe I went too fast. And I want to refer a few papers. This one is actually a very review. Probably Roland will also mention others in the field. Here is a paper where we start to discuss this charge, valley, spin, Hall effect in presence of disorder. And I also point out DFT calculation of the value Hall effect in presence of disorder. So it's very unusual that we can tackle with first principle and with disorder together, but this is an interesting paper. Okay, we have 15 minutes for questions, so thank you for your attention. Let's have some questions.
Questions?
So the last plot you showed was a simulation or measurement?
Experiment?
This was experimental, right? Or?
Okay, no.
Okay.
Unfortunately, no, all simulation.
Okay, so can you say what's the reason that this valley polarization at the K point is not completely zero if it's simulation? Is it the approach matter, or do you still observe some current, right? Or this conductivity at the K valley?
Yeah.
What's the reason for that?
Because with the real magnetic field, we broke time reversal symmetry. Okay, it is superimposed. But at the same time, we have, singularized valley K and valley K prime. Okay, so it's kind of, difficult to imagine that, you have part of your electrons that see no gauge. They are completely, it's completely silent in one valley, but at the other valley, you have another type of effective magnetic field which can be detected experimentally. Okay. So that's because of the uniqueness of this time reversal symmetry conserving pseudomagnetic field. And as far as I know, this is, of course you will say, how can you generate this pseudomagnetic field with strain, with low value? Because if you want to use an external magnetic field, you don't want 1,000 Tesla or 10 to the 6 Tesla. For technology application, that's completely crazy and stuff like that. But theoreticians, we can think about that, but experimentally, I think they're more clever. And chemists, in particular, more clever than we are. So they can find a way, maybe, to have a superlattices of small pseudomagnetic field, which can be switched on and off in different values and so on.
Okay, thank you.
This question.
We have another question over there.
Thank you. So this seems really sexy.
Sexy, fancy,
sexy, scientifically.
Okay.
But like not like applications, but can you envision how you might use something like this? Like is like a valley polarized source, or have you thought about in a sort of a scientific context how it might be usable?
I don't know. I mean, if we will be very optimistic, we could say if you have such a superlattices and generating this pseudomagnetic field, then it could be a sensor of a magnetic field, okay? Because we really have an observable consequence. So if there is a small magnetic field, then that can come into play. It could be detected through transport. It could be without. So we can always be like super optimistic, but magnetic sensor, this is not my real field. But I could say like that. If there is a magnetic field, very, very teeny, but that will play the game on what I've been talking about, then it could be detectable by whole conductance measurements. Yeah.
Sounds good.
Yeah. So you measured your whole conductance in absence of magnetic field because it's not, and then maybe something happened. There is a very small magnetic field that emerged, and then because of your pseudomagnetic field, you probe it. Like that could be, but you know, I don't know. I mean, this is this journal is maybe not so fancy or easy to read or whatever. People don't know. So for experimentalists, they usually look at PRLs to see for their next IDs. I hope you could make it. You know 2D material actually very well.
Okay. Further questions?
So what I can say that also, because I have still time, is that from an optical point of view, I think Roland tomorrow you will enter into the optoelectronics and things like that. From an optospintronic point of view, this Valley spin locking and transfer information from excitons to spin and to you detect this non-locally. This is just fascinating, and I don't know if Roland will enter into trying to explain his measurement. I would wait, because it's just transfer of information. You shine light in a certain polarization, and then you detect a spin with a certain spin polarization. So you transfer information, and I think that that's probably. I think that's probably the easiest way to engineer more complex manipulation of degrees of freedom. But a problem with the electric readout is that I don't know other. Maybe you make the edges zigzag and then you suppress one of the valley or something like that. But I don't know how can we do to detect the presence of a Valley polar's electric signal. So this is an example. It looks like also science fiction, maybe not for theoreticians, but for experimentalists. But it's a real possibility, just because these pseudomagnetic fields are very special, and they, as far as I know, nobody has argued against the possibility to engineer them and to observe them. Okay. So.
Indeed, I have a question about these pseudomagnetic fields. So these are local magnetic fields, are localized, or but then you see like
yeah, question, yeah.
So this pseudomagnetic field is a local magnetic field, but from the outside world you see like a global magnetic field.
You agree? Yeah, it's a good question. In this configuration where you have a superlattices, they will superimpose. Okay, so you will have your local pseudomagnetic field is actually at a certain extent in space and spatially. So they superimpose, and then they're all the same. So they make a global magnet.
Okay,
indeed, if there was just one bubble and 10 square meter graphene, all what I'm saying is not. It's completely crazy, right? So we need this extended pseudomagnetic field, of course, not just local.
Questions? No?
People are tired of listening to me.
Okay, so then we thanks again.
Thank you.
Stephan,
Thank
for the
you.
talk.